Well, that's kind of a version of seatbacks and tray tables that I guess we've all missed, huh?
Yeah.
So how many of y'all are returning? Can I get a show of hands? And hands down, how many of y'all are new? Well, to the new folks, welcome. To the returning folks, welcome back. It's really great to be here, really great to be back. Second survey question on this topic for today before I really get into it. How many of you are carrying either a 16-inch or a 14-inch MacBook Pro M2? Hands way up. Okay, so 4, 5, 6, 7 of us. M1s? 13-inch or before Intel? Okay, I just wanted to kind of get a survey question. One of the reasons that's important, we'll find, is because of hardware platform support differences that Apple has with respect to different forms of Wi-Fi. So welcome to what I'm calling 2.6e, Further Developments in Wi-Fi. My name is Chris Dawe. I am CT Dawe in the Slack. I am a Seattle-based IT consultant specializing in Apple and networking. Co-developed a one-day Wi-Fi workshop with Tom Bridge that we've delivered several times here at Penn State Mac Admins and a few other locations, X-World, the Cascadia IT Conference, etc. Also, founding board secretary of the Mac Admins Foundation, and as of the COVID era, unintentional parent to a pair of Abyssinian guinea pigs named Persimmon and Mr. Pickles. Today's agenda, we are essentially going to talk about what we're calling Wi-Fi 6 and Wi-Fi 6E in an effort to distinguish and demystify the two. We're going to talk about the implications of Wi-Fi 6 and Wi-Fi 6E especially. We're going to talk about Apple's moves in Wi-Fi recently as relates to Wi-Fi 6E. And then we're going to kind of establish kind of a baseline of where we are and talk about what next, what now kind of thing. So, Wi-Fi 6, what is it and where did a number come from? Well, the Wi-Fi Alliance is a nonprofit that controls Wi-Fi trademarking, and over the last few years they've looked at the kind of the alphabet soup of IEEE standards and decided that it might be simpler to brand generations of Wi-Fi for simplicity, and so they created a generational numbering scheme. They labeled what we call 802.11ax as Wi-Fi 6, and then they started working backwards through the most recent of the, quote, modern Wi-Fi amendments, 802.11ac, which they call Wi-Fi 5, and then 802.11n, which they call Wi-Fi 4. They didn't bother trademarking 3, 2, and 1, but people use those labels anyway. Fortunately, most of those technologies have essentially been superseded and retired, so for the most part, we don't really pay too much attention to those in the day-to-day world anymore. So Wi-Fi 6, or 802.11ax, was an effort started a few years ago to bring a greater amount of efficiency to Wi-Fi in an effort to improve its overall performance. And what this really meant was that instead of just trying to make the numbers bigger, trying to go from, say, 100 megabit Ethernet to gigabit Ethernet, we were looking at ways in which we wanted to reduce some of the implicit waste in the Wi-Fi world, and really kind of increase performance by increasing overall efficiency and, quote, decreasing waste. There's quite a lot in my campfire talk from 2020 about kind of the details of this, but I do want to cover each of the pieces or several of the pieces of this, each briefly. So in previous versions of Wi-Fi, you had what's called orthogonal frequency division multiplexing. And in that, a sending device sends a single data payload to a single destination and a single transmission. Over time, practical experience showed that in many scenarios, a system would often end up sending smaller chunks of data than the minimum size of a Wi-Fi frame or a Wi-Fi packet. So for the transmission, there was a lot of wasted space. You essentially pad out the packet with nothing in order to make the delivery. Think especially of things like voice over IP, where you have to deliver a lot of frames very quickly, but the amount of data being sent is very small. This presents us with an efficiency problem, and that you have the full frame size, but the frames and the transmission opportunities are underutilized. You can think of this a little bit like an underloaded pickup truck. Sure, this truck is going to carry this backpack, but doing so isn't very efficient use of its capacity. It would be more efficient to load this thing up with the backpack, the plywood for this month's Home Depot project, the family groceries from Costco, what have you. Get all these things delivered in one trip. And so Wi-Fi 6 replaces, or at least supplements, OFDM with what we call OFDMA, standing for Orthogonal Frequency Division Multiple Access, which is on the grand tradition of making the same letters stand for something slightly different. The theory behind OFDMA is to aggregate multiple payloads into a single transmission that can be heard and received by separate and discrete clients. Because loading up a single payload from multiple destinations essentially reduces our wasted transmission opportunities. To belabor the analogy a little bit, you fill the back of the truck up and you send it to multiple destinations. OFDMA accomplishes this by taking the 20 megahertz channels that we're so familiar with in Wi-Fi and subdividing it into slices called resource units, and then allocating various resource units or groups of resource units to multiple payloads within a single transmission. The slide on the screen shows an example of what we call downlink OFDMA, where an access point loads up multiple payloads and sends it in a single transmission so that it can be heard by multiple clients. OFDMA in the downlink mode is at least somewhat common now, whereas its sort of companion OFDMA upload, where you're attempting to coordinate multiple transmissions from multiple clients to a single AP, is something that requires a lot more in the way of coordination and computational power and hasn't really arrived yet. The second big feature of Wi-Fi 6 was going to be what's called multi-user MIMO, transmission to and from multiple clients. There was a version of multi-user MIMO included in 802.11ac, Wi-Fi 5, which didn't see much adoption because, again, very complicated to actually make work. In this iteration of multi-user MIMO, an access point with multiple radio chains can split the use of the radio chains to transmit to multiple clients simultaneously. There are two versions of this, downlink and uplink, depending on which direction you're sending. Uplink in particular requires significant management and coordination from the access point to pull off. And again, this is one of those things that, it's great in theory, not quite used yet. Third big feature of Wi-Fi 6 is what we call BSS coloring, which is a scheme that's designed to help client devices distinguish between different Wi-Fi cells that are using the same channel. Historically, a client that could hear two different APs on the same channel was required to treat both as possible sources of contention and cooperate with both in efforts to avoid collisions and transmissions. BSS coloring attempts to mitigate this by introducing labels called colors that are applied to the various access points, the various BSS IDs, and adds some programmatic judgment about how to treat stronger versus weaker signals. This is a fairly loose illustration on the screen in which a client is associated with the red access point, but it can understand, even though it can hear the blue access point, that the blue access point signal is pretty weak, and that therefore it shouldn't pay too much attention to the blue access point in attempting to determine whether it's contending for airtime or not. So essentially, we're taking some of the rules and finding them a way to just break them a little bit. And then finally, we have what's called 1024 QAM, which is a way of modulating and encoding data. This is an increase from 256 QAM in 802.11ac/Wi-Fi 5. Essentially, what it says is we're encoding more data, and because we can encode more data more efficiently, the end result is that we can get some new MCS rates with this encoding, MCS 10, MCS 11, and that on its own increases our data rates by about 25%. So this is the one that has really sort of shown up because this is the one that fits in with kind of the traditional way of dealing with transmission. So in theory, at least, what AX accomplishes, or Wi-Fi 6 accomplishes, is an overall data rate increase potentially of 37% over AC. And when you get really complicated and you start thinking about a Wi-Fi network as a holistic system instead of just one client or one access point, theoretical calculations show that all of these improvements should be able to improve the aggregate performance of a network by something like 300%. And unfortunately, that's really hard to measure. And it's also the case that in the real world, a lot of these technologies haven't really been delivered to Wi-Fi 6 clients. They're dependent on both the access point vendors and they're dependent on the client device vendors. And if you take a look inside probe and association requests coming from clients, you can see that a lot of the time these features aren't enabled on clients at this point. And so it's a little bit frustrating because famously, the Wi-Fi industry is, very big on these big numbers, 300% improvement, 37% improvement, big asterisks that says all of these features must be available on both the client and the access point in order for this to work. And one of the things that we find is that various client vendors don't always develop for those features. I think I watched a presentation from this year's Wireless LAN Professionals Conference where one of the companies that does Wi-Fi network monitoring talked about the fact that their monitoring sees a lot of 1024 QAM on the network, so they see that in use. They see a fair amount of downlink OFDMA, that is multiple aggregate transmissions being sent from access points, mostly to voice over IP phones. So there's a lot of efficiency gains there, but in terms of the overall market, it's been much more mixed bag. And in the meantime, the whole industry started moving into this newly opened but relatively unexplored chunk of spectrum with Wi-Fi 6E. So what's the distinction with Wi-Fi 6E? When we say Wi-Fi 6E, we are talking about implementing the 802.11ax protocol, that is, the Wi-Fi 6 protocols, in a new frequency band that was previously unused by Wi-Fi. This new band consists of 1200 megahertz of total spectrum, ranging in frequency from 5.9 gigahertz to 7.12 gigahertz, that the US FCC approved for unlicensed use starting in April 2020. And if you're thinking, well, so the Wi-Fi Alliance took our nice, clean generational branding and jumbled it a bit. Yes, they did, and we'll live. In any case, 1200 megahertz of spectrum in the 6 gigahertz band represents more than twice the total available spectrum in the 5 gigahertz band. Wi-Fi 6E brings us a grand total of 14 80 megahertz wide channels, along with a specification that only the 802.11ax PHY mode is allowed to run in the 6 gigahertz band. We're leaving 802.11ac and 802.11n behind in kind of the legacy 2.4 and 5 gigahertz bands. Comparing the 6 gigahertz band and its available channels to the 5 gigahertz band, the 14 80 megahertz channels that we have in 6E or in the 6 gigahertz band compares pretty favorably to the 580 megahertz channels that we have available in the 5 gigahertz band, especially when you consider that 3 of the 80 megahertz channels in the 5 gigahertz band are subject to DFS rules. Who knows what DFS rules are? Okay, a few of you. So one of the things that's not commonly understood about the 5 gigahertz band is that it's essentially sliced into two broad chunks of channels. There are channels that are not subject to what's called dynamic frequency selection, and there are channels that are subject to what's called dynamic frequency selection. What this means is that if you're running your access points in a frequency that is subject to DFS rules, your access points are required by the federal government to listen for radar signals that the access points might be interfering with, and if they detect one at a significant enough signal threshold, your access point is required to drop all connections immediately and switch channels. And it does this without warning. It'll usually log it, but you can imagine how this goes with respect to a network that's depending on your Wi-Fi for voice over IP calls. So DFS has been kind of one of the big asterisks in previous generations of Wi-Fi. And the fact that over in the 5 gigahertz band, we only had 2 80 megahertz channels that didn't require you to switch if you detected a conflicting non-Wi-Fi signal, that really constrained what we could do with the 5 gigahertz band. And kind of implicit here is that whereas the 5 gigahertz network band has historically required us to sacrifice pure data rates in exchange for spectrum efficiency and reducing conflict between clients and access points in favor of sort of narrower channels in favor of channel reuse, we have a veritable cornucopia of channels in the 6 gigahertz band, and that takes us in a different direction for a few reasons. In the 6 gigahertz band, that is in Wi-Fi 6E, 80 megahertz channels with their larger data rate possibilities are not just feasible from a spectrum reuse standpoint. We're also going to see that there are specific technical reasons why effective design will benefit from them, and the whole industry is actually kind of leaning into wide channels, leaning into 80 megahertz channels. And that's going to be interesting to watch. Beyond these kind of questions of channel widths and data rates, some of the odd limitations, regulatory issues that we've dealt with in 5 gigahertz just kind of drop away in the 6 gigahertz band. Dynamic frequency selection requirements, terminal Doppler weather radar rules, all of which kind of hobbled our ability to design really high performance networks in Wi-Fi in 5 gigahertz. Those are just gone in 6 gigahertz. They're not really considered to be a factor. So we're finally in a position where spectrum limitations no longer force us to sacrifice the bandwidth of our connections in exchange for spectral or channel efficiency in order to be good Wi-Fi citizens. And that also means that I can stop yelling at you in person and on Slack for deploying 80 megahertz channels when you really should be deploying 40s or 20s or what have you. That's kind of a famous tradition of this conference. I'm doing 80s, don't do that. Questions so far? Anybody? Anybody? Yes?
Are there any concerns, or is there any kind of signals that the 6 gigahertz band could potentially?
Yes, and we will talk about that. We'll talk about what are called incumbents in the band and what's being done to address those. Back in the back, the mask.
Are those 80 mega
Shh.
channels non-overlapping?
Sorry, I forgot the catch box, y'all.
Can you hear that? Okay.
Yeah, absolutely.
So those 14 80 megahertz channels in Wi-Fi 6, are they non-overlapping?
They are non-overlapping. It's a wide open. It's greenfield. It's beautiful if you can find beauty in that kind of thing. Next question.
In the 80 megahertz channels, you're saying they're preferred. Is there a reason to use a smaller one? Is there better connectivity, like for VoIP applications that certainly don't need that wide of a channel?
That's a good question. I'm not entirely clear on whether there would be a good justification to go to narrower on an application by application basis. What we'll see when we continue is that a lot of the reasons to go to 80 megahertz for channel widths are kind of side effects of how much spectrum we really have. The fact that we have, if you sit down and you look at the numbers, that 12 1200 megahertz of spectrum gives you 59 20 megahertz channels and 14 80 megahertz channels, and whatever the in-between is for 40, I don't have it in my head. And that has some interesting effects on some of the administrative tasks in Wi-Fi. Things like scanning for networks becomes a bit more onerous, and we'll talk about that. Anybody else? All right, let's have the catch box back. So what's the catch? With all these advantages, what's the catch? Quite a catch, that catch-22. There's a lot of catches to this. And for the most part, they're not bad. It's just an issue that you're coming upon kind of a generational change in the way that this is done. A lot of the rules that we have are going to kind of go out the window. They're going to be replaced by new rules, and we're going to see at least some new snags. So, one new snag. Anybody in here own a Sidekick or some kind of other spectrum analyzer? Like Ekahau device, Y-Spy, anything like that? Well, all of those were built for 2.4 gigahertz and the 5 gigahertz frequency band. So if you're doing Wi-Fi design, right now you're working on your budget to upgrade to 6 gigahertz capable equipment. You know, a general spectrum analyzer for Wi-Fi tends to come in right around $1,000. The Ekahau Sidekick is something like $2,000, $3,000. So if you're doing a lot of diagnostic work, you suddenly have a budget issue that you have to look at in order to replace a lot of this equipment in order for it to be compatible with 6 gigahertz networks. So what's next? Configuration requirements in 6 gigahertz. Those have bitten me a couple of times. I've only set up a few 6 gigahertz networks, but you know, the same sets of requirements have kind of led me to some forehead smacking moments both times, 3 times. One is that WPA3 security is a hard requirement in 6 gigahertz. If you have, say, a network where you've enabled WPA3 transitional security, and you go and try to assign it to the 6 gigahertz band and hope that it'll show up, I think in that particular case, for me, that dropped everybody's network. Dropped the 5 gigahertz as well. The access points got very, very angry. So look for that WPA3 requirement to be a strict requirement, whether it's WPA3 PSK, pre-shared key, or WPA3 enterprise. You're going to be on WPA3. So if you are thinking in terms of deploying Wi-Fi 6E, you want to start looking at testing that now for compatibility with all of your devices. The other thing that's a little bit of an implicit requirement, and I talked about this a bit, I got burned by it actually last week while I was testing for this particular talk, is that 802.11ax PHY mode is a hard requirement as well for Wi-Fi 6E in the 6 gigahertz band. Back when Wi-Fi 6 first shipped, there were a lot of concerns around compatibility with clients, and so most of your hardware vendors gave you the ability to go in and flip a checkbox on your network that said turn off 802.11ax, and a lot of us did that out of kind of stability concerns or because we were mixing and matching APs with older generations, things like that. You're going to have to go in and find that and turn that back on in order for your network to work in the 6 gigahertz band. But yeah, take a look at this. This is a view of the 6 gigahertz band. This is where my middle-aged eyes start to feel really, really insulted. Wi-Fi Explorer Pro has been supporting the 6 gigahertz band, and you can see all of our channels in the 6 gigahertz band ranging from 1 all the way up to 233. One of the things that's a little wonky about this is that in the 6 gigahertz band, the designers and the folks who decided what the channels were going to be called felt like it was okay to just go ahead and reuse some of the existing channel numbers from the 2.4 gigahertz band and the 5 gigahertz band. So you're going to see some repetition in there that might ultimately be confusing, cause you some documentation issues. I'm not aware yet of whether there's kind of an officially accepted designation for channels that distinguishes them. So for me, I would probably write something like Wi-Fi 6, And what do we have? Yeah, we have 165 here, we have 160, we have all of these in the 5 gigahertz band too, and they're all different frequencies, different channels. So you'll want to be careful on that. And the width of this thing, the total number of channels and frequency available here are going to kind of bring us to questions of network discovery and how our clients find our networks. We got 59 available channels in 20 megahertz, or 59 available 20 megahertz channels in 6 gigahertz. There's a total of 25 in 5 gigahertz. And one of the little sort of known facts about the 5 gigahertz band is you're not allowed to actively scan the DFS channels. So when you're scanning for networks on a traditional Wi-Fi environment that consists of 2.4 and 5, you're scanning the 11 2.4 gigahertz channels and somewhere between 8 and 10 5 gigahertz channels. And so, 19 to 20 versus 60, if you were going to scan the 6 gigahertz band as well, you're essentially adding, 3 times as many channels, so all of a sudden your scans take 4 times as long as they used to. It's too many channels to actively scan them all. Furthermore, one of the other things that we often do is we often passively scan, which means that our clients just kind of sit on the network and periodically listen for transmissions from the network to try to detect access points so that they can build their list of access points without having to go out and check. Again, we have 59 channels, and in order to capture an access point in a passive scan, we've got to dwell on each channel for 100 milliseconds. And that means that a full passive scan just to the 6 gigahertz band is going to take us 6 seconds, which, 6 seconds is very short in some senses of time, and it's very long in other senses of time. Certainly when you're talking about, how do I switch channels when I'm in the middle of a voice over IP call or a Zoom call, 6 seconds is going to be an eternity. So what do we do about this? What Wi-Fi 6E does is it has kind of a mishmash of solutions that are still kind of in the process of being implemented to see how well they work. One thing that we've done, and I'll drop back to this, and this is going to be barely visible. Every 4th channel in our channel list down here is colored in kind of a pink-red color. That designates those channels as special. They're what's known as preferred scan channels, PSCs. And essentially what we've done is we've taken the 59 channels we have, we've sliced it into groups of 4, and we've designated one preferred scan channel for every 4 channels. And so instead of scanning all 59, we'll scan just those 14 or 15 preferred scan channels that speed our scans up. A second way that we're doing this is that we're having client devices and access points, we have access points make more announcements about their availability, and we have clients pay more attention to those announcements so that clients are more proactively building a list based on what our access points are saying. And then finally, and most importantly for today's purposes, we advertise our 6 gigahertz access points, 6 gigahertz information in the beacons for the 2.4 and 5 gigahertz networks. So essentially, as we scan our existing legacy networks, our existing legacy SSIDs in 2.4 gigahertz and 5 gigahertz, one of the pieces of information that we're getting from those networks is, hey, 6 gigahertz is over here. This is what we got for 6 gigahertz, go over here. If you dig into a beacon frame, and in some ways this is marginally understandable in terms of the technical details for me, but if you look for information element 201 in a beacon frame of either a 5 gigahertz access point or a 2.4 gigahertz access point, you'll find what's called a reduced neighbor report, which, if there's a 6 gigahertz network present, will advertise information about that 6 gigahertz network so that your clients can find it without actually having to go and scan the 6 gigahertz band. Yeah, there's giveth, taketh away kind of thing, and looking to the kind of the concept of suddenly having all this spectrum available, and then the concept of, whoa, now we have to look at all of this spectrum. Get this back there.
So for the preferred scanning channels, does this also require like coding on like the operating system side to actually actively be scanning for this as well?
It does, yeah. This is one of the things that comes up with respect to supporting new technologies and new bands is, are your client devices and their drivers being coded and written to address this? And sometimes the answer is yes, sometimes the answer is no. One of the things that is, I would call a bit unclear and a bit confusing around all of this right now is that some of our favored vendors aren't really documenting what they're doing yet. We'll talk about that a little bit later. You can read what documentation is available and you may be able to infer some things, but the thing that we're actually having to go out and do, and I'll concede I haven't done a lot of this personally yet, the thing we're actually having to go out and do is we're actually having to go out and run packet captures, read logs, find out what it is that these things think they're doing, how it is the other things are reacting to that, and what's the behavior. And we'll see when we talk about Apple, there's some stuff in Apple's limited documentation for Wi-Fi 6E support that makes you think, it's not so much about Apple, it's that everybody's kind of rushing into this and nothing is really fully baked yet. We're still trying to figure this out. Other questions? Okay, so fourth issue we have to look at, and I believe you raised this earlier, is the issue of incumbent technologies in the 6 gigahertz band. A lot of the initial discussion of the 6 gigahertz band made it sound like this is just a wide open play field. Spectrum is full everywhere. It's contested for all the time. Whenever you open up spectrum, there's almost always an incumbent who's sitting there. In particular, there is a lot of fixed microwave networking, satellite and broadcast TV, things like that live in the 6 gigahertz band already, and that presents its own set of problems, but we're choosing to address it differently in Wi-Fi 6E than we did in Wi-Fi 5, or Wi-Fi 6 and before. Sorry about that. In Wi-Fi 6 and before, we were working with this thing called DFS, again, where we detect a signal that's not Wi-Fi, we drop off the channel and switch channels and hope for the best. In Wi-Fi 6E, we're doing a couple of different things. One is that we're designating differences between power levels of transmission, indoor and outdoor. We have what's called low power for indoor, and all the channels are available indoor. We're doing what's called standard power output for outdoor, and we're chopping off a couple of the bands in the 6 gigahertz spectrum and saying you're just not allowed to use these when you're working outdoors. So the 6 channels in the Uni 6 band and the 14 channels in the Uni 8 band, or I guess subband of this spectrum, are not allowed to be used outdoors in order to avoid potential interference with incumbents. The other thing that we're doing is it's kind of fun and it's kind of absurd. We're doing another cloud database, and we're doing a thing called automated frequency coordination. The mechanisms for automated frequency coordination, and again, right now this is specific to the United States, not sure how other countries are handling this yet. We're gonna require that outdoor access points operating in what's called the standard power will operate under the control of an automated frequency coordination system. This is essentially a planned location lookup database in which access points are going to report their location, and the database is going to tell them what channels they can and cannot use based on other registered users who might conflict in that frequency band, TV transmitters, things like that. The way I understand it, the construction of this database is still underway. The mechanisms are still under development. And so right now, 6E, I think, is not officially supported outdoors in the United States. I was doing a little reading on this last night, and I think the most recent things I found were the federal government submitting requests for proposals to start to develop this database a year or two ago. So this is underway, and this will get there, but it's not there yet. Moving on, next and fifth potential issue around Wi-Fi 6E. Has anybody deployed a 6E access point yet? They're big, aren't they? They're heavy. And you don't really realize how heavy 3.5 pounds is until it comes to you and you have to hang it on a T-rail underneath drop ceiling. They're beefy. They serve an additional frequency band, and the thing that's interesting about this is everything is additive here. We're not replacing anything, we're just supplementing it. We're taking our 2.4 gigahertz access point, 5 gigahertz access point, we're adding another radio to it, so it gets bigger, it gets heavier, the antenna requirements change. Transmission also changes. This is a side-by-side of a Cisco 9164 in the 5 gigahertz band and the 6 gigahertz band at the same relative power level. And so something to be aware of is, along with the kind of big beefier access points, you may have some issues in coverage. Broadly, the way that I read the Wi-Fi community right now is that those issues in coverage tend to be small enough that you can tune by adjusting power output settings on your access points. They're not considered to be super significant, but at the same time, when you're doing your design, suddenly you have 3 bands to design for. And one of the things that we've always talked about when we talk about design is if you're really focused on 5 gigahertz Wi-Fi, you want to focus on 5 gigahertz design because that's really the high performance band. Now that we're coming into the 6 gigahertz band, we have a decision to make about, are we going to focus our design on 5 gigahertz? We're going to focus it on 6 gigahertz. At the very least, you have to take all of your bands into consideration. You don't just get to drop the old bands, because as we've seen, most of our clients are going to use 5 gigahertz or 2.4 gigahertz to discover 6 gigahertz anyway. So you don't get to just walk away from it. Your design process becomes a little bit more complicated and probably a little bit longer in terms of working with your network professionals as well. Together with that, we get into some infrastructure issues around our design. Network vendors have been pushing multi-gig Ethernet for a long time, and they do it by kind of looking at the top potential speed of a Wi-Fi link, which is usually lab-based, theoretical, and to quote our president, malarkey. So there's a lot of kind of pushing for what we call multi-gig switches, where you're deploying Ethernet with a bandwidth per port of 2.5 gigabits or 5 gigabits. And we'll see in a minute what the maximum throughput on Apple devices is gonna be, but in testing, we've seen people use the maximum width channel, 160 megahertz in Wi-Fi 6E, to finally achieve a more than 1 gigabit Wi-Fi connection in the real world. Are you gonna see that in your deployments? Probably not. Probably not, because you're probably not going to deploy 160 megahertz channels due to spectral reuse issues. Another issue that kind of pops up is that these theoretical speeds, they're very much lab-oriented. As soon as you start adding devices to the network, you start to increase the management overhead of the network, and you start to decrease the potential throughput of the network because management overhead it starts to take over a little bit. And so I don't really consider the need for multi-gig switches absolute. But this is something that you want to think about, especially, is anybody involved in your equipment life cycle for networking in your institution? Do you have a set equipment life cycle for switches?
Yeah, when they burn out.
Okay. Do we have a scheduled equipment life cycle? Anybody got a scheduled equipment life cycle? 5 years? Okay. So some organizations use 5 years, some organizations use 7, some organizations use 10. And this discussion of multi-gig is one of these places where your equipment life cycle and your network team's planning becomes kind of important, because it's very possible, particularly if you're in a very stable kind of budget-oriented institution, that you've got a very predictable life cycle. We replace our switches every 7 years with whatever the best thing is or the second best thing is. We replace them every 10 years. We do not deviate from this life cycle. And so as you think about whether you're going to deploy or when you're going to deploy something like Wi-Fi 6E, I've been pretty harsh about this multi-gig Ethernet thing in the past because, again, so much of the Wi-Fi marketing is just malarkey in terms of what the maximum potential performance is. But ultimately, we're going to have Wi-Fi 7 coming down the road with higher potential throughput, and at some point, we may actually hit that point where you can exceed a gigabit of speed in a sustained way coming off of a wireless access point. I don't think it's really realistic right now. Is it realistic in 5 years, 7 years? If so, do you want to think about just going ahead and making the investment in the multi-gig switches so that you're not constrained when you reach that point? That's an internal business discussion for you and your team and your institution. I think that for a lot of my customers, I probably wouldn't, but I'm also not someone dealing with, big bureaucratic institutions. So it's very much something that you want to start to think about as you start to look at a possible Wi-Fi 6E deployment, because at a certain point, your life cycle on the switches is just going to be very predictable, and you're going to have to get the best thing you can at the time, or you're going to have to wait until 2033 to do it again. Question, where'd the catch box go? Catch box.
So actually, another thing I was just thinking about with this was your infrastructure wiring too, because if you're just replacing APs with new APs and you're going to put your switches in with multi-gig, like I have a Fluke tester, but that only tests up to 1 gig. So now you've got to test your cabling for multi-gig, functionality, and if that fails, you got to build that wiring cost into your job as well.
Yep, that's absolutely correct. And you got to my next slide for me. Why don't you toss that back up here? So yeah, you have other things to think about in terms of your general overall network infrastructure. Newer access points require newer, more powerful power over Ethernet standards. That also cascades onto your switches. If you're not paying attention, it also cascades onto your cabling infrastructure as well. I think some of the more recent higher powered PoE standards require higher end cabling in order to support the power throughput that PoE is going to require. I think that, I believe we have PoE++ in 2 different variants. I didn't get the second one onto the slide. I believe that the power delivery or the power delivered from the port, I think on the second variant of PoE++, is 90 watts, which is about the same wattage that you get in the fast charging adapter for a 14-inch MacBook Pro. We're going to be delivering a lot of power. Cabling's going to have to change. Your switches are going to have to change. Conduit will probably have to change because the cabling gets thicker and sort of the curvature characteristics are different. You fit fewer cables in a conduit. The power delivered to your network closets will have to change because the switches will be putting out increased power. Cooling, thank you. It all kind of has a cascading effect. And when you go to look at all of this, be very aware that there are really, when you talk about power over Ethernet, there are really three figures that you care about in terms of the power consumption of your wireless access points. One is there's how much power is a PoE port going to deliver under a given standard. Typically, there's also a maximum power rating, that is the maximum power your access point vendor says that the access point is going to draw, that you should be using for kind of your budgeting and your network design, because you know that the access point should never exceed that figure. And then three, and the dangerous piece, the thing that's really easy to get a little bit, smug is the wrong word, a little bit, I need another word, but if anybody let me know.
Laissez-faire.
Yeah, a little laissez-faire about it, thank you. About is that the third figure is how much is the access point actually drawing? And this is a really good example of a Cisco Meraki access point that says, hey, my maximum power requirement is in the range of 15 watts, but in day-to-day usage, I'm only using 4.7. And so if you're not careful around design, you're going to end up in trouble by assuming that you get away with less power draw than you might actually get away with now that you're trying to power 3 radios, or in a lot of access points now we have Bluetooth radios, we have security radios, more and more and more. One thing that you'll run into is that a lot of these access points will intelligently attempt to step down the power of their feature set if they're provided with less power than they're spec'd for. So you might find that an access point that was supposed to deliver 4 spatial streams is only delivering 2 because the power over Ethernet is insufficient. So all things to be aware of. And all of this adds up to a requirement that if you start looking at deploying a dense 6 gigahertz network using new access points, you're going to probably end up, especially if you're a large institution with large network closets and very tightly designed power and cooling budgets, you're going to be having to take a look at your MDF and IDF infrastructure in order to make this work and not create problems for yourself. So, a lot of catches. Most of them are manageable with appropriate planning. Most of them are manageable with awareness of what you're getting into and good work with your infrastructure, network, and facilities teams. There is a fair amount that you have to get into with respect to things like planning your cells, replacing your tool sets, understanding that network discovery is going to be different. Hopefully you're going to do something like some limited testing in one building to see how this behaves. But I think that most of this is fairly manageable. So now that we've been through that, we've been through Wi-Fi 6, Wi-Fi 6E, let's talk a little bit about what Apple's moves in this space have been over the last few months. Over in there's a Wi-Fi professionals Slack, and I think it's fair to say that Apple catches a lot of flack in that Wi-Fi professionals Slack for being kind of slow to move into these markets. And I think there's a context in which Apple is a company that, unlike a lot of other vendors, is going to be running out millions and millions of devices per year. And so Apple moves very deliberately when adopting new technologies. At the very least, I think, and again, all personal opinion, I don't have any special inside knowledge, that if you're going to ship 100 million iPhones, you need to be ready to build 100 million iPhones. And you need to be ready to move those out the door, which means you have to establish the supply chain, which in turn means that the supply chain has to be somewhat mature. And if there's anything we've learned in the last few years, it's that supply chain maturity is something that was maybe a little oversold to us in a lot of ways. So Apple appears to be moving deliberately and strategically to transition to Wi-Fi 6E as they introduce new generations and models of devices. So, Apple devices that support Wi-Fi 6E, the MacBook Pro M2 14-inch and 16-inch models, none of the M1s, none of the M2s in the older M1 case are going to support that. Fourth generation of iPad Pro, which was, I think, released in October, was the first device. The M2 MacBook Pros were in January. At WWDC, Apple announced 6E, 6 gigahertz support in the Mac Mini and the Mac Studio, and the forthcoming Mac Pro 2023, so that when you take it and put it on its wheels, it'll stay connected to the network no matter where you move it and how far you move it and how fast. I have ambitions to use a Mac Pro in the next generation of my roaming talk. I think that would be a lot of fun to do a live demo. Anyway, equipment that is not supporting Wi-Fi 6E to this point. Any of the MacBook Airs, either the M2 or the MacBook Pro, or the previous 13-inch MacBook Air M1, MacBook Pro 13-inch in any model, any of the non-Pro iPads, iPhones, Apple TVs. Apple's platform deployment guide documents their general overall specs. And one of the things that's kind of interesting about this is that the specs are relatively compact in the platform deployment guide for Wi-Fi 6E devices. They're all, by all appearances, using basically the exact same chipset across the product line. They're all capable of an MCS index of 11 for high efficiency. They all have 2 spatial streams, so they can send out 2 separate streams of data for resiliency of the signal. Maximum channel width supported is 160 megahertz. And as a result, the maximum PHY rate, or data transmission rate, on those connections is theoretically 2,400 megabits. And so again, this is where you see a place where you could potentially exceed 1 gigabit. And something you always have to keep in mind here, and this is basically a Wi-Fi 101 thing. The transmission rate with respect to actual data throughput is, a lie is the wrong word. It's a specific technical term that doesn't reflect what actually goes on. Because Wi-Fi is effectively a half-duplex medium where only one device in a cell can transmit at any given time, it has the effect of approximately halving the maximum transmission rate in order to arrive at what your maximum potential throughput is. So if we say, as in this slide, that on an 80 megahertz channel, our maximum potential data rate is 1200 megabits, when we test this in the real world using file transfer tools or iPerf or speed test or what have you, what you actually find is the actual data transfer rate ends up looking more something in the range of 600 to 750 megabits. The TX rate that you see at the top of the screen when you option click is never the number that you get in terms of actually moving data. And that's just a baseline understanding in Wi-Fi. It's something that you want to be aware of. And it tends to, what you actually get tends to depend both on kind of that math of dividing by 2 because it's half duplex, and also network overhead and contention issues. So you can see a TX rate at the top of your screen on your Mac of 1200, and it's well conceivable. If you told me I'm only getting 150 megabits in speed test, I'm like, how busy is your network? I'm not surprised, because the TX rate is a little bit of it's a baseline. It reflects what your client device thinks it can do, barring any other considerations, any other interference considerations, contentions considerations, overhead considerations, etc. So you want to be kind of careful with that. It is a lot faster. 600 megabits is pretty respectable, but keep in mind that even with all of these improvements, Wi-Fi is still Wi-Fi, and it's still sort of constrained by some of the limitations of Wi-Fi. So, Apple documentation. Apple has published a short, somewhat mysterious document describing best practices for Wi-Fi 6E. It outlines, fundamentally, it says three things. One is it iterates through the list of supported clients in Apple's product line. The second thing it does is it explicitly states that for compatibility, a network has to have 2.4 gigahertz and 5 gigahertz enabled on it. Apple's not going to support a 6 gigahertz only network. So if you go out and you buy your 6 gigahertz access points, slap them on the ceiling and turn off 2.4 and 5, Apple's saying we're not going to work with that. Anybody have a guess as to what that's implying? Those are some cups right there. Oh, I tend to underthrow, I apologize.
I was actually going to ask about this because 2.4 and WPA3 and IoT devices are not going to play nicely. And my guess is it's going to decide when it feels like connecting to Wi-Fi 6.
Yeah, I think that's part. You're getting at the answer to the sort of the question I'm posing. The real question is, why do we have 2.4 and 5 on as a precondition for 6 working?
Apple HomeKit.
Okay, well, that's not the answer. What's that? So my answer to this is presumably that Apple is relying on that 2.4 gigahertz and 5 gigahertz access point discovery in order to find the 6 gigahertz network. What I'm reading for that is that if you don't have a 2.4 network or a 5 gigahertz network saying, hey, here's the 6 gigahertz network using a reduced neighbor report, Apple's not going to find it. So you got to have 2.4 and 5 on. Don't run out and turn those off. I mean, as you correctly pointed out, there's all this IoT stuff out there. There's all this legacy equipment. For the most part, you're not going to be running out to turn that off anyway, but almost certainly someone will. And they're going to call AppleCare and they're going to complain. And so that's what this article is for. The other thing that Apple is advocating for, and they use a little bit squishier language in this particular discussion, is that they strongly recommend using the same SSID across all 3 bands. That is, if your network's name is the Great God Ohm, and you want the network name to be the Great God Ohm on all 3 bands, and a lot of systems allow you to change the SSID names per band or enable certain SSIDs only on certain bands. I'm a little more unclear on what this might be about, but to me it sounds like a relatively similar kind of issue, some kind of discovery issue. Apple says in their article that if your SSID names are not the same across all of your bands, Apple's operating systems will offer you the choice, connect to 6 gigahertz with the possibility of reduced performance, or connect to 5 gigahertz and be on kind of the legacy 5 gigahertz band. I tried to duplicate this before I came out here with a Cisco Meraki network. I set up a 6 gigahertz SSID that was not on the 2.4 or 5 gigahertz bands. I couldn't reproduce what was in Apple's article using my Mac. So I think that there's a little bit more exploration required here.
They offer it with HomeKit.
Okay.
That because a lot of IoT devices are only on 2.4.
Yep.
The 5 gigahertz band. Sorry.
Let's start over. Underthrow.
HomeKit really dislikes when your phone is not on the exact same SSID as any of the controllers.
Okay.
And if you try to use Siri for personal requests on a HomePod and your phone's not on the same network,
So what I'm hearing here is that there's a possibility that Apple is implicitly messaging some of their non-Wi-Fi technologies and implicitly messaging compatibility and ease of use of some of their non-Wi-Fi technologies with respect to how it interoperates with Wi-Fi. That's an interesting point. You're so much better at that throwing. And then I think finally, Apple's article explains to you that you can go into your system settings on either a Mac running Mac OS Ventura or in iOS, iPad OS, and you can go in and on a per network basis, if you're having trouble with Wi-Fi 6E, you can disable Wi-Fi 6E on a particular SSID. I don't know that they've actually, those of you who are doing Manage Macs, one of the questions that I expect to be asked and I do not know the answer to is, can we do this with a profile? I don't know the answer to that yet. I looked in Apple's profile documentation, I didn't see anything like this. Sometimes it takes Apple a little while to catch up in terms of profile management keys. Maybe we'll see it, maybe we won't. Questions?
Regarding the profiles, has feedback been filed for that?
I have not. I bet we can find out. Oh boy. All right, we're gonna do a relay thing again, Ben.
You mentioned cabling. What specs are we looking at? Cat 6? Above?
I'm not going to try to answer that question specifically because I haven't looked at it recently and I'll almost certainly be wrong. I feel like I remember seeing 6A specified for at least some of the higher level PoE standards. That's a step up from 6. I think it has, it's thicker, it's heavier, but it's something that we're going to want to dig into. I don't really know the answer on a per standard basis at this point. But a lot of, especially larger institutional organizations will tend to have installed whatever the minimum possible to meet the standard was at the given time. So you may find, I still find Cat 5 in a lot of places, and in a lot of places I have a hard time justifying replacing Cat 5 because it'll run gigabit Ethernet. What else do I need to do? It runs the 2 PoE standards that I generally need. So every project's going to be an investigation. Every project's going to require a little bit of discovery around that. And I'm sorry I don't know that answer, but it should be pretty easy to find. Anybody else? Send it back up.
So we've rolled out Unify with 2.5 gigahertz and Wi-Fi 6, and industry group that I'm a part of kind of, castigate's the wrong word, but they're like, oh, you should have waited for 6E. I'm kind of curious what people who are considering 6E are chasing. Is it just better reliability for more users, or are there specific applications where trying to get to a certain speed? I mean, I don't think anybody's going to be editing 4K video over an iSCSI connection through Wi-Fi. So what?
And you'd be surprised what I've been asked to do. You're both right, and you would be surprised.
I'm just curious, what applications are we chasing for people who are thinking about 6E?
Does anybody want to try to? I mean, I have my own answer to this, and this is where we get into kind of the holistic discussion of like, what are we trying to accomplish here?
We're in the midst of looking at replacing our system. Beginning stages, our Wi-Fi and our switches, because they're both old at this point. And so, when you talk about these new standards coming out, for us it would be future-proofing. So if we're looking at buying a new system, if there's one that's only 6 but not 6E or whatever, yeah, that's for right now, but we may not need 6E now, but we may want it in 2 or 3 years. To the point of what Apple devices support 6E. Right now, none of our devices that we use even support it, but that wouldn't hold us back from trying to get a 6E network, because the next round of devices that we get in 2 or 3 years almost guaranteed will support 6E.
Right,
So,
right. And what I would argue is probably your organization or your institution is going to have something like a 5 to 7 year budget life cycle on your network infrastructure.
Yeah.
So you're
Wi-Fi
again,
at least 5. Switches are more like 7 to 10.
Yeah. You're looking at future, as you said, future proofing right now. Why don't you? Oh, got somebody in the back.
I just wanted to go back to the wiring and kind of what you were saying. The other thing you have to be careful of is building code. we've been notified in New York City that building code is going to start encompassing PoE++ and the next as
Interesting.
high voltage
Okay.
instead of low voltage wiring. Because they're starting to deliver so much, that changes the standard of the jacket around it, changes where you can mount it, and everything. And it basically what we're doing is we're looking at distributed switches so that all of the PoE++ is short, and then using fiber between the
Okay.
switches
Okay.
because fiber is so much cheaper
Yeah,
now.
that's a really interesting implication. If you're suddenly pushing enough power to power a MacBook Pro through an Ethernet connection, you probably can guess that the building inspectors are going to be a little troubled by the potential of that. So I have my answers for why you would do this. One is that why would you look at going to Wi-Fi 6E? What's the justification? The real one is the increase in non-overlapping channels that are not limited by things like DFS rules. That is, you have arrived at a place with 6E where you actually have enough 80 megahertz channels to really run a sequential network design of AP, 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 AP without repeating your channels, reducing the sort of potential that your network is effectively going to interfere with itself through contention. I think that's the big deal here, is that wide open spectrum, we've not ever had anything like it before. We have lived as Wi-Fi people in kind of a world of compromise, again, around data rate performance versus spectral efficiency and not interfering with ourselves and others. I'm a little bit less clear personally on data performance metrics, how much data you're actually trying to push through the connection. One thing that's true is that I think a 4K Zoom meeting with 2 or 3 screens requires something like 6 or 8 megabits per second, which is substantial, but it's not 600 megabits. Certainly if you can push 600 megabits, you potentially increase the efficiency of those meetings, the number of people who can be on a meeting in a Wi-Fi cell before you bang into limitations, but you're also limited by your transmission airtime in that case as well. And so pure bandwidth isn't necessarily the thing that you're worrying about in those cases. For me, it comes down to kind of spectral efficiency and being able to design channels without having to make these compromises along the lines of, well, sure, I can use 25 channels, but 16 of them offer the possibility that my VoIP callers are going to be kicked off with no notice. That I think is really what it's about. I do think that the 80 megahertz wide channels are kind of a side effect, it's like, oh, now we have to scan all that spectrum. How do we deal with it? Let's just make the channels wider. There's a little bit of hand waviness to it, but it's early days. Wi-Fi 6E is going to flood the market. The products are rolling out now. With some of the supply chain issues that I've dealt with the last couple of years, I've deployed some Wi-Fi 6E access points from Cisco because that's what I could get, and because the customer needed them now. But Apple's product line isn't complete. My personal guess is that within a year, Apple will have 6E in at least some product in every product line. I'm a little more skeptical that they'll roll it out through all of the product lines. It's possible that we'll see something like Wi-Fi 6E in the iPhone Pro and Wi-Fi 6 in the lower market or lower tier iPhones, whatever you want to call them. It's anybody's guess, really, but based on the pattern, that's what I would predict. And I'm willing to bet the proverbial cup of coffee on it, but I'm not willing to bet real money. Couple other important comments. Your 5 gigahertz network that you have that works is not obsolete. Well-designed 5 gigahertz network will continue to do what they're designed to do. There's currently no imperative that I can see to sunset that equipment unless you're moving into a budget or a replacement cycle, or unless you have a specific business need. Wi-Fi 6E brings some pretty impressive benefits in the right scenario. High density environments where there's significant channel contention, problems with overlapping networks, environments where higher bandwidth could bring, significant performance benefits. Again, remember that you have to replace the clients too to get there. And no matter what, you're still going to be managing a 5 gigahertz network with implementations as they are. There's just too many legacy devices, and we're depending too heavily on 5 gigahertz and 2.4 gigahertz networks for discovery of the 6 gigahertz network. So what I would say is budget for Wi-Fi 6E, start planning for it. Don't rush it ahead of your replacement cycle without a good business reason. Try to be smart about it. And in all likelihood, next year it's going to be cheaper and it's going to work better than it does already. Questions?
I'm just kind of curious. I had a question. It's we lived without Apple monitors for 5 years, and then they came back. I'm just kind of curious if you think Apple will ever get back into the base station, and also implications for 6E. I know we've been talking about enterprise, but for residential, you're a consultant.
So yeah, I mean, I think, okay, so that's really two questions. I have no strong opinion about Apple and airport base stations. I kind of suspect not, because I feel like what Apple did with airport base stations was, Apple does a couple of things. One is they sort of bring out a mass market product and sort of popularize a mass market product. It's one of the reasons that I think that the Wi-Fi community gets a little salty about Apple's slow roll into Wi-Fi 6E, is because, and this is where I get a little salty, because after years and decades of kind of feeling abused by people saying my Apple device is not a real computer, it's the Apple devices that are really sort of pushing forward the requirements, because there's just purely so many of them now. They're so popular. But at the same time, I think that sometimes what Apple does is popularize something and then kind of step back from that market. You've got your Eero, you've got your Netscape Orbi, Google has their Nest stuff. There's just so much kind of very popular, relatively low cost, home market targeted equipment that I think Apple would need to see a reason to be in that market, and I can't conceptualize what that would be. Again, I don't work for them. All my opinions are just kind of, listening to my experience and speculating based on my experience. But I wouldn't expect that. What was the second question?
Just implications for residential. And
Okay.
To answer your question, why Apple would do it is it's still harder than it needs to be.
Yeah.
To set this stuff up for a residential user.
Okay, so you're saying it would be it's harder than it needs to be to set stuff up for a residential user, and I think that right now I'm not in a place to sort of talk about that intelligently. I think that I think that Wi-Fi 6E will be good for the home market. I sit at my house and look at the frequency bands in my little complex of townhouses, and I have purchased a couple of enterprise access points for my house, and I deliberately put them on DFS channels because every one of my neighbors is using either a Comcast or a Lumen cable modem, and they're all configured exactly the same way, 80 megahertz channels and one of the two chunks of the 5 gigahertz band that are available to non-DFS users. So I took my access points and threw them on DFS, and I have no competitors for my network spectrum, which is a fancy trick if you know how to do it. But I think that a larger number of those 80 megahertz channels will certainly ease some of that issue that you see, especially in ultra-dense places like cities, townhouse developments, condos, things like that, because instead of having two 80 megahertz channels that everything is going to sit on, you can have 14 for them to compete for. The real issue is going to be making sure that those hardware vendors are smart enough to pick from across all 14 instead of just landing on one or two of them. That would be my opinion.
It looks like category 6A is the correct cabling to support that.
So what I'm hearing is that the category 6A cabling is the correct cabling to support PoE++. Which is, come on, where did that? 60 watts of output from the device and 51 delivered to the device. Is there any mention of the 90 watt variant or whatever it is? What's that? Oh, you haven't seen that? Okay. All right. Well, we'll just table that. How about other questions? We're down to 2 minutes. I actually kind of can't believe I filled the time.
How do you think WPA3 is going to affect the home?
I don't know enough to have an opinion on WPA3 in the home. Wait, who?
I was just gonna say, based on this article, it says for 90 watts output, 73 input.
90 watts output, 73 input. Does it say anything about the cabling? Because that's really the question.
Switches come in type 3 and 4, which output over Cat 5 cables, it says. I'm not sure if it.
That sounds wrong. All right, that sounds like a mass market article. I suspect that's probably not going to be what you're looking for. I'm down to 44 seconds before the music starts. Was there one last question?
So how much of this is, this seems to be driven by the American market, but how much of this do you expect to be implemented internationally or slower rollout?
It's starting to be implemented internationally. The issue is that each country or whoever the regulatory authority is has to approve it. I think we've seen some approvals. We've seen some limited approvals in Europe. Europe has approved a smaller chunk of the spectrum, and it's going to vary country by country. I suspect that with respect to Canada, you'll probably see it in Canada because I feel like Canadian authorities and American authorities tend to mirror one another. And that's it for the time. Thank you so much for coming.